All right, let's talk about a feeling every developer knows. You push a new feature, everything looks good, and then suddenly a completely different service starts throwing errors. Or maybe you try to load some old data from your database, and boom, your app just crashes. What's going on? Well, a lot of the time, the real culprit isn't your logic. It's something way more fundamental, how your data is encoded. We're going to dive deep into how the way we structure our data is literally the foundation for building systems that can actually change and grow without falling apart.
You know, it's funny how a quote from ancient Greece nails the biggest problem in modern software engineering. The whole point is, our applications are never done. We're always adding new features, squashing bugs, and shipping new code. So if we know that change is the only constant, we absolutely have to design for it right from the start. Otherwise, we're just building on quicksand.
Okay, so here's how we're going to break this down. First, we'll get into why change is such a big deal. Then we'll compare the classic text formats versus binary ones. After that, we'll unlock the power of schemas, looking at two big players, and then a really cool alternative called Avro. We'll tie it all together with how this stuff works in the real world, and finally, help you figure out which approach is right for your system.
All right, let's jump right in. So why is this stuff so critical? I mean, really, why can't we just update things and move on? Well, think about a modern deployment, a rolling upgrade. We're not taking the whole site down, right? We're updating our servers one by one. And for a few minutes, or maybe even longer, you're in this wild state where you've got both the new code and the old code running at the same time. The new code is writing data, and the old code has to be able to read it. If it can't, well, things go bad. Your old code sees this new data format, has no idea what to do with it, and it just falls over. This is exactly why compatibility isn't some nice-to-have feature. It is absolutely non-negotiable.
So, to get through that messy rolling upgrade, you actually need two kinds of compatibility. The first one is what we all think about, backward compatibility. It's pretty straightforward. Your brand new code has to be able to understand the old data that's already sitting in your database. No problem. But here's the one that trips people up, forward compatibility. This is the really tricky part. It means your old code, the stuff that's still running, has to be able to handle data written by the new code. It doesn't have to fully understand it, but it has to be able to gracefully ignore what it doesn't recognize. If you don't have both, every single deployment you do is basically a ticking time bomb.
So how do we actually pull this off? The answer starts with the format we choose to encode our data in. Let's take a look at the usual suspects, and you'll see why some of the easiest choices up front can lead to some massive headaches later on.
Okay, first up, a serious warning. You know those handy built-in libraries in languages like Python's Pickle or Java's Serialization? They seem super easy to use, right? Well, they're a trap. Seriously. First off, you're immediately locking yourself into one language. Good luck getting your Java service to read something your Python service pickled. But it gets way, way worse. This is a security nightmare waiting to happen. These libraries can often execute code, which means a clever attacker could send you a piece of data that, when you try to read it, runs malicious code on your server. So, let me be clear. Unless you're just passing some temporary data around inside a single app, just don't. Stay away from these.
Okay, fine. So we're not going to use those language-specific things. What about good old JSON? Everybody loves JSON. It's readable, it's universal, but it has some sneaky little problems. And this example from Twitter is perfect. See, tweet IDs are huge numbers. They're 64-bit integers. But here's the catch. The JSON standard doesn't actually have an integer type. It just has number. And a lot of things that read JSON, like JavaScript in a browser, will see that big number and try to treat it like a floating point number, which can mess up the last few digits. It loses precision. So what did Twitter have to do? They send the ID twice, once as a number, which might get mangled, and once as a string, which is safe. When you see a workaround like that, that's a huge red flag that the format itself has a weakness.
And that weakness brings us to the real solution, using a schema. Think of a schema as a blueprint or a strict contract for your data. It says, this field is a string. This one is a 64-bit integer. This one is an array of strings. There's no guesswork, no ambiguity. And the undisputed kings of this approach are schema-driven binary formats. The two you'll hear about most are Google's protocol buffers, everyone just calls it protobuf, and Facebook's Thrift. They're designed to solve both the ambiguity problem and the size problem all at once.
So to really see the difference, let's use this simple person record as our example. Super basic, right? We've got a name, a favorite number, and a list of interests. We'll see how this same piece of data looks in a few different formats. And right away, check out the first huge win. Size. That simple person record takes up 81 bytes as JSON. Okay, now you could use something like message pack,
which is basically binary JSON, and you get it down to 66 bytes. Better, but not amazing. But look at protocol buffers. 33 bytes. 33! We're talking less than half the size of the JSON. Now you might think, who cares about a few bytes? But when you're talking about millions of API calls a minute or petabytes of data in a data lake, this isn't a small optimization. It's a total game changer for cost and performance.
So what's the magic trick? How do they get it so small? Well, here's the secret sauce. Field tags. Look at this protobuf schema. Instead of writing out the full field name, like username, which is 8 characters long, over and over again in the data, it just uses the number 1. Instead of favorite number, it uses the number 2. The actual encoded data is just a super compact series of tags and values. It doesn't contain any of those long, repetitive field names. That's the core idea that makes it so incredibly efficient.
And these tags aren't just for saving space. They're the key to evolving your schema safely. The rules are actually pretty simple, but you have to follow them. If you want to add a new field, easy. Just pick a new tag number that you've never used before. Old code will see this tag it doesn't recognize and just skip right over it. Boom, forward compatibility is handled. Now, what if you want to remove a field? You can, but, and this is the most important rule, you can never, ever reuse that tag number again. Ever. Think of the tag as being retired forever. Because if you reused it for a new field, newer code might get old data and think tag2 means email address when it used to mean favorite number. That's how you get catastrophic data corruption. Okay, so protobuf and Thrift are all about these permanent tags. But what if I told you there's another, equally powerful way to do this that doesn't use tags at all? Let's talk about Apache Avro. This format came out of the big data world, the whole Hadoop ecosystem, and it has a completely different philosophy.
The core idea behind Avro is brilliant. It separates the schema that was used to write to data from the schema that you're using to read it. Let that sink in. With protobuf, the tag numbers are the shared secret language between the writer and the reader. With Avro, there is no secret language. Instead, the data itself says, hey, I was written with this exact schema. We call that the writer's schema. Then your application comes along and says, okay, well, I expect the data to look like this. That's the reader's schema. And here's the magic. They don't have to be the same. As long as they're compatible, the Avro library acts like a universal translator between the two.
So here's how that translation, or schema resolution, actually works. Your code tries to read some data. The Avro library grabs the writer schema that's packed with the data, and it compares it to your code's reader schema. And here's the key difference from protobuf. It matches fields by name, not by a tag number. So if your reader schema is looking for a field called username, and the writer schema has one, great, they match up. What if your reader expects a new field, say email, that the old data doesn't have? No problem. As long as you provided a default value in your schema, Avro just fills it in for you. And if the old data has a field your new code doesn't care about anymore, it just gets ignored. It's incredibly elegant.
So why is this no tags approach such a big deal? Well, it's a total game changer for any situation where your schema isn't static. Think about dumping data from a database. With Avro, you can literally write a script that looks at the database table and automatically generates a perfect Avro schema from it. Tomorrow, a DBA adds a new column to that table. What do? You just rerun the script. That's it. Now think about doing that with protobuf. Someone would have to manually open the schema file, add the new field, and, most importantly, carefully pick a new tag number that has never been used before. Avro completely automates that away, which is a massive win, especially in big data pipelines.
Okay, enough theory. Let's talk about where the rubber meets the road. How does all this apply to the actual systems we're building every day? When you look at modern systems, you'll see data flowing in pretty much 3 main ways. First, you've got data flowing through databases. This is your message to your future self. You write it now, and who knows when it'll be read again. Second, you have data going through services, like a classic REST API or an RPC call. This is immediate, back-and-forth communication. And third, you have asynchronous message passing. This is where you fire off a message to something like a message queue and just forget about it. Some other service will pick it up and process it whenever it's ready. Each of these patterns has its own unique challenges when it comes to evolution.
Now, when we're talking about service calls, we have to touch on a classic trap that a lot of us fall into early in our careers. It's called the RPC illusion. It's this idea that you can make a network request look and feel just like calling a local function. But you can't. A network is a messy, unpredictable place. A request can get lost, it can get slow, it can time out. And when it times out, you're left guessing, did my request even make it to the server, or did it work and the response just got lost on the way back? If you just blindly retry, you could end up doing the same action twice, like charging a credit card twice. A senior engineer understands this. They know you have to embrace the unpredictability of the network and design for it, usually by making your operations idempotent. That's a fancy word that just means you can safely run the same operation over and over without changing the result after the first time.
And what about databases? This is maybe the most important point of the whole explainer. Data outlives code. I want you to really think about that. We can deploy new code in minutes. We can completely replace every single line of an application. But we can't just replace our data. That record that was written 5 years ago, using a schema from 5 years ago, it's still in there. And your code today has to be able to read it. This is why for anything you put in a database, backward compatibility isn't just a good idea, it's an absolute ironclad rule.
Okay, so we've covered a lot of ground. How in the world do you choose what to use? The biggest takeaway here should be that this choice isn't some minor implementation detail you leave for the last minute. This is a fundamental architectural decision. The format you pick is going to dictate how easy, or how painful, it is for your system to evolve for years to come.
So let's wrap this up with a quick cheat sheet. If you're building a brand new internal service and you need speed, go with gRPC and protocol buffers. It's fast, it's strongly typed, it's the industry standard for this kind of thing. Building a public API for other people to use, stick with REST and JSON, but use a schema like OpenAPI to make it official. The tooling and community support are just unbeatable. Working on a big data pipeline, pulling data out of databases, Avro is your best friend here because of how well it handles those dynamically changing schemas. And finally, for the data you're actually storing long-term in a database, you really need the guarantees of a schema, so pick either Avro or Protobuf. You'll thank yourself in 5 years.
And that's a wrap. So I want to leave you with one final question to take back to your own projects. Look at the way you're encoding your data right now. Is it a silent enabler of change, letting you move fast and build new things without fear? Or is it a roadblock, a source of hidden friction that makes every single deployment feel like a gamble? The choice matters, and its effects will stick with you for a very, very long time. Thanks so much for joining me.